Good afternoon, ma'am. I am here to discuss the different types of circuits. Number one, in your own words, define the following. An intrinsic material, pure semiconductor, also called an adaptive semiconductor or E-type semiconductor, is a pure semiconductor without any significant dopant species present. The number of charge carriers is therefore determined by the properties of the material itself instead of the amount of impurities. B. A negative temperature coefficient. NTC refers to materials that experience a decrease in electrical resistance when their temperature is raised. Materials which have useful engineering application usually show a relative rapid decrease with temperature, i.e. a lower coefficient. C. Covalent bonding. A covalent bond is a chemical bond that involves the sharing of electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs, and the stable balance of attractive and repulsive force between atoms when they share electrons is known as covalent bonding. So number 2, describe the difference between N-type and P-type semiconductor materials in terms of added impurities and carriers. The impurity added in P-type semiconductor provides extra holes known as accept or atom, where areas in N-type semiconductor impurity provides extra electrons and termed as donor atom. In a P-type semiconductor, the majority carriers are holes and the minority carriers are electrons. Sketch the difference energy gaps of insulator, semiconductor, and conductors. Explain the difference among the three materials. Number 3, sketch the difference energy gaps of insulators, semiconductors, and conductors. Explain the difference among the three materials. So here the sketch, guys, ma'am. Here the sketch of a conduction band is EV, and EQ is equal to 0 valence band, conductor, semiconductor, electron energy, and insulator. Conduction band, electron energy, and electron energy EC. E. In conductors, valence band and conduction band overlap each other. In semiconductor, valence band and conduction band are separated by a small energy gap. In insulators, they are separated by a large energy gap. B. In conductors, large number of free electrons are available in conduction band. In semiconductor, a very small number of electrons are available for electrical conduction. In insulators, conduction band is almost empty, i.e. no electron is available for conduction. Number 4, describe what happens in a p-n junction diode with respect to the depletion region and current flow. So E. Depletion region. Our depletion layer is a region in a p-n junction diode where no mobile charge carriers are present. Depletion layer acts like a barrier that opposes the flow of electrons from inside and holes from p side. B. Current flow. A forward bias p-in junction conducts a current once the barrier voltage is overcome. The external applied potential force majority carriers toward the junction where recombination takes place, allowing current flow. A reverse bias p-n junction conducts almost no current. No bias. When a diode is zero bias, no external energy source is applied, and natural potential barrier is developed across a depletion layer, which is approximately 0.5 to 0.7 volts for silicon diodes and approximately 0.3 of a volt for germanium diodes. While in integrated circuit, the PN junction then materials is called forward bias because the electrons move forward into the holes. If voltage is applied in the opposite direction, a positive voltage connected to the N side of the junction, no current will flow. While when a PN junction is reverse bias, the negative terminal of the battery attracts the free holes in the p-type towards itself, whereas the positive terminal attracts the free electron in n-type towards itself. So here is the sketch of no bias and forward bias or reverse bias. So this is a conventional current flow or current throughout a silicon anode. So here's the sketch of the tree, a current in no bias and forward bias and reverse bias. So that's all, and thank you.